relatively straightforward. So I'll look just at section 8.1 real quick, a little bit. I don't think on the homework sheet I had homework there, did I? I think it was to be announced. I can't remember now. But if I do have homework, ignore it. It's fine. So what's funny is we talk about finding volumes after rotating these shapes. And, that's kind of interesting. It's really a little bit weird. There's a lot of details to be careful about. This idea is kind of taking it way back. If I have a function, little piece of a function, let's say, and I want to know how long that is. So I'm not rotating it, I'm not finding the area under it, I'm saying how long is that? Now let me let you just think about that for a minute. I mean, can you see why on the surface of it that would be kind of a difficult question? I could estimate it, sure, I can see how long this is and say it's going to be a little longer, but I want to know exactly how long that sucker is. Okay. So, weirdly enough, we do use integrals, and the thing we have to start to realize is the very first thing we use integrals for is to find areas between the x-axis and a function, right? That's the very first thing we use it for. Let me see what I get as an answer to this, if I get any answers at all. Tell me what an integral is. What's the most basic definition of what an integral is? And don't just say area. There's something more basic than that. Where'd it come from? Why is it a big ass S? It's just a big S. No, it's not why it's a big S. Some, I heard there were some, but there's a word that's missing though. That's why it's an integral, not just a sum symbol, right? Sum symbol versus big ass S. What's the difference? There you go. It's an infinite sum. So anytime I have an infinite number of things and I want to add them up, I'm going to use an integral. So at the beginning, and this is a useful tool, is to kind of remember integral does mean area in a very fundamental sense. It's connected to the area. But once we develop the process, we start to realize, we can use it in other ways. I can set something up that represents the volume of an area with this one-dimensional kind of integral statement. That's kind of nifty, I always thought. And then I can start to realize, it's not just area, it's adding an infinite number of things up. That's what it does. So if there are an infinite number of little rectangles, then that's going to give me the area. If there are an infinite number of little pieces of this line, it's going to give me the length of the line. So really, we start to focus our attention on how do I represent a little piece of this line. So let me focus. Let's zoom in on a piece of this. Let's zoom in on just this piece right there. Whoop. Okay, so from here to here, how long is that? Well, let's see now. What's this and what's this? Okay, I should have zoomed in more. Let me do it even more. Here we go, Jeff. So this is basically straight in the middle. You guys cool with that? Because I zoomed way in. If the more I zoom in, now obviously the function needs to be continuous. If it has breaks in it, I can just split my integral up. Does that make sense? If it kind of does this thing, I just split the integral up between those. Okay, maybe. So when I zoom in on a little piece of this, it's going to be straight. We saw that. That's the whole idea of linear approximations. It's a line when it's close if it's differential. Okay, now, what is this? Let me just I'll take almost anything. What is that piece of this? And I am zoomed in. Let's say I've zoomed in an infinite amount. Okay? So what is this? Do it. What's changing along that direction? What's changing in this direction? If we go from here to here, what's changed?
Distance of x.
Yes, x is changed. And I told you we zoomed in infinitely. So this would be dx. So you should be able to, what's this? dy. I like it. So how long is this? Not what's the slope. Don't tell me dy over dx. That's the slope. I want to know how long that piece is. And of course, what have I created here? By definition, I've created a right triangle. So how long is this piece? Yes, good. So it's the square root of dx squared plus dy squared. Let me stop for a second. I love this idea because it's just almost too simple to believe. So all I want to do now is add those up. I've just defined every piece of this, every little piece of this looks like this. That's how long every little tiny infinitesimal piece is. So how do I get the whole length of this sucker? I just integrate. I add up an infinite number of things. How do I do that? Integrate. That's what it does. So what would this look like? This is still missing something. I'm missing something. And what's really, really cool is, watch where this comes from. What am I missing? Anybody see there's something fundamental missing for this symbol to work correctly? Yeah, what's the d what out here, right? You guys with me? So let's factor a dx out. Because what's the square root of dx squared? What's the square root of dx squared? Dx. I love it. So let me see if you guys are cool with this. If I take a dx out, if I take a square root of dx squared out, this of course becomes 1. What does this become? Just divide by dx squared. So it becomes that. And I'm integrating from, I can see now that I'm integrating from a to b because I've chosen to take the x out. If I would have taken dy out, I could have integrated from f of a to f of b. The whole idea of I can shift whichever way makes more sense based on the function I'm working with. Is it easier in terms of x? Is it easier in terms of y? I chose to take a dx out so then I can say from a to b because it's a function of x. If they gave me a function of y, I would just take a dy out and then it would have been dx dy squared plus 1. dy outside. What is dy dx? What's another symbol I could put there? What's dy dx? What's the quicker symbol we use? dy dx. In terms of what's f of x related to dy dx? That would also be known as, using this, what's dy dx? What's the other way to write dy dx? No. F prime. Okay. So then the length, the arc length of this, the length of this piece of the function is equal to the integral a to b, square root of 1 plus f prime squared. So if they give me a function, I take its derivative, I throw it in there, and I integrate this. Do you guys notice something, though? Depending on what the function is, this could be a very difficult, maybe impossible for us integral to do. You guys realize that? Whatever f prime is, whatever f is, it better be a function that comes, it's a big-ass square root on that sucker. Most of those I can't do. You should be able to answer this question. What is missing for me to be able to do this integral? Knowing what we know. In the first 2 weeks in Calc 2, you would learn how to do this quick. But right now, we don't know that shit. What's missing? Can anybody tell me what's missing? Think about it. Think about it. What would you want to use here? What method would you want to use? U sub. What would U be? What would du be? 2x dx. So what are you missing? An x. And I can't give it an x. I can do constants all day. Constants can come in and out. X, this is the frickin' variable. I can't take it in and out. I'm screwed without. If this was here, doable. If it ain't there, not doable. So do you see how that form could lead to a lot of situations where we don't know how to integrate? I like it. But the idea of how to set this sucker up is Pythagorean theorem. It's like, to me, it's so beautiful. It's so easy. But again, if you came in after I said this, I'm not going to... Some of you guys realize, are like, oh man, I wish you were doing some of these. But we're not. I'm not going to make this something you have to do. Okay? But I just wanted to give you this idea because it's gone over again in later calculi, and then you can kind of build off of this very basic idea. But this is something that's really cool to see, this idea that you can use these really are just lengths. They are lengths. They're infinitesimally small, but they're still lengths. And that kind of opens up a lot of other things we can do. So in further calculus courses, you start to realize how much flexibility and interpretation there is, and you're able to do more and more things based on understanding what the integral is and what the parts can do. Okay. So I needed to get that out there in case anybody's going on in the calculus series. Let me see. Let me catch up with people that just came in. Oh. All right, so that was it. That was the last new thing for the semester. It's crazy. Just to make sure everybody sees, the office hours during finals next week. All that really matters to you guys is that I'm in my office from 6 to 7:05 before the final on Tuesday. Monday's a holiday. It kind of sucks, because then everything's closed for help. That's, oh shit. Okay, so I want to open up, I want to have today and Thursday for review. So it's time to unleash with any questions about anything that you want to go over. We can do some practice final stuff if you want to just start working on the practice final. Yeah. Yeah. So on Thursday. Thursday's the last day of class. I'll have an answer key for the practice final. That would be evil if I didn't. I'm like, figure it out. The actual final, I think this came, I can't remember if somebody asked this in this class, but our class runs for a little over 2 hours. I know I let us out early every day because they don't give us a break. I don't know if you guys agree or not with that, but nobody's ever brought it up. I just want to let us out early instead of getting a break. But the actual final exam then cannot be longer than one of our normal tests because we still only get 2 hours for the final. You guys with me? So I'm obviously going to have to streamline it a bit. But what exactly will be on it? Could be anything. So obviously I can't tell you because you have to know everything. That's all. So now it's wide open. Whatever you guys want to look at, discuss. Yes?
Can we either go over number 5 or do a problem similar to number 5? On the practice final?
Well, why don't we all try to do number 5? That's one of the hardest problems, I think, is being able to set it up and figure out how to get relationships. So you have to draw that picture out for yourself, figure out what the relationships are. Just give you a clue. You want to represent a general location of the water. And that's where you give it variables. But you're going to have 2 variables. So you have to come up with some relationship between the 2 variables. So what I always do, if I'm dealing with a cone and I suck at drawing, which you all know is a true statement, then I just draw a triangle for myself, and that's good enough. It's basically a slice through that. If you are a good artist, you can show off. Draw me a little cone. So this is the drawing I would use. What variables do you need where? What is it in this picture that's changing? I've given it somewhere, but what's changing? The amount of water. So what's changing in my picture are going to be this length and this length. That's why I have to give them variable expressions. Right? What are these for? Well, that's what they tell me. So this is basically a tell me, ask me problem. Anybody remember the volume of a cone? On the final, if I give you one of these, I'll give you the volume function, but hopefully somebody might remember. Yes. Pi r squared h is a cylinder, and I make a cone by cutting 1/3 of that cylinder out. There's a cone. That's when it's 1/3 the volume of the cylinder. How many variables are in that expression? Let me say it like this. How many variables is volume a function of? 2. See, that sucks. So this is what they ask me about. And what is it they tell me these things? What am I going to label this with, of course? We already kind of gave it a letter, to be honest. Physically, what does this represent in the picture? What does this represent in the picture, physically? What am I interested in this problem? I know there's a cone there, but what am I really interested in? The water. So that's the volume of H2O. I say water weird, sorry. So this represents the volume of the water at a certain time, right? So what is this going to be? I've already called it R, and I've already called this H when I wrote that equation down. Now, do you really have to call them R and H? No, but, you know. Now we've seen this situation before, and this is the most common situation to see in these kind of problems. How do I use what I know to help me with what I need to work with? How to use what they tell me to help me with what they ask me? What can I do here? I have too many freaking variables over there. Can I figure out what one is in terms of the other one? Somehow. What have I created here? I've got two triangles. What kind of triangles are they? Similar triangles. That is one of the most common things to happen. I'm not saying it's going to happen in the final. I'm not saying it's everything. I'm just saying that's one of the most common kind of things to happen. So what can I set up? What can I set up here? There's a lot of different ways to do it. I got a little triangle and I got a big triangle. So the ratio of the big triangle stuff equals the same ratio of the small triangle stuff. Or you can do the ratio of the heights equals the ratio of the radii. It doesn't matter. That's the kind of thing you look for, and you can't look for that kind of thing if you haven't drawn a picture at all, or if your picture isn't drawn well at all. And when I say drawn well, this is barely a triangle. I know I suck at drawing, but I've represented what I know, what I don't know. I've done that. That's why it's a good drawing. I can then see how things are related. Now let's see how far you can get. Keep going. You've got everything you need. Let me make sure. Which letter are you solving for here, considering what they tell me? What are the symbols for what they tell me there? They tell me, what's that 2 centimeters cubed per second? What symbol goes for that? What symbol represents 2 cubic centimeters per second? That's how the what is whatting. Volume is changing. So what symbol is that? We put it over here. dV dt equals 2. Okay, cool. And what else did they tell me? H is 5. So what letter do I want to stay alive here? What letter do I want to keep? Considering what I know. What do I know something about? Height. So what letter do I want to stay alive over there? No. H. I know H is 5. So I want to keep H alive so I have somewhere to put 5. Now do I have to do that? Could I figure out what R is if H is 5? Sure. But just using what they told me, I want H to stay in there because they told me what H is. Plus, what are they asking for? What are they asking for? dH dt. So double reason why I want H to stay alive, because I need to be able to solve for dH dt. Do you guys see this? This is exactly what you have to consider. And it's not difficult. What do they give me? What do they ask me? Let me make sure that what I set up gives me a way to answer what they're asking me. That kind of makes sense. If they're asking me DHTT, I better have a DHTT show up, meaning I want to get rid of R. So how do I get rid of R? How do I use this to get rid of R? Solve for R. I love it. Right? So R equals 3h over 10. All right, so see how far you can get now. Keep going. This is that related rate stuff that we wanted to do forever. Pretty cool with that? You know R. So you put it in. So now I have volume as a function of height, which is good because I know something about the height. I know the volume, how it's changing, and they're asking me about this. So of course the next thing I do with this is, take the derivative so I can have a place to put all this stuff. When you do this side, what has to show up? Because I'm not taking the derivative with respect to h, I'm taking respect to t. So when I do this, of course, what's going to happen? What's the derivative of this side? The only variables there.
How come you're not putting in 5?
If I plug in a constant before I've taken a derivative, everything is 0 in the universe. I need to know what the relationship is between how the volume is changing and how the height is changing, and then I plug stuff in. So this is why it's called related rates. Are volume and height related? Yes. Then if I wanted to know the volume for a certain height, I would just if I plug a 5 in, I'll know what the volume is right then. Right? So everybody cool with that? So if I put a 5 right there, I would know what the volume of water is when the height is 5. It's not what they're asking. They're asking me what's dH dt. If I put a number in right now, everything's constant. Derivative is going to make it 0. Really? So you've got to take a derivative first. You have to get a derivative function, and then you can plug stuff into it, right? So we know this. If I ask you to find if I give you a function and I say, what's the derivative at, let's say 4 squared, at 2. You don't put a 2 in and then take a derivative, right? Do you guys see that? Because if I put a 2 in and then take a derivative, it's 0. Everything is 0 in the universe. And we all live in caves. I mean, we can't go anywhere then, right? So I have to first create the function that talks about rates of change, and then I plug stuff in. So don't use the snapshot information too early. I've got to get the correct, I don't care about the volume, I care about the change in volume. Right? That's what I know something about. So I have to first get that function set up, then I plug specific stuff in. Is that cool? I mean, was a huge thing when we first did this, because that's what's going to happen. If you plug stuff in too early, everything's 0. It's not changing at all. I pour water into this cone, and then I go around the country magic show. You know, that magic trick where they pour water in, and there's no water. It doesn't change. No. So here, what happens? What do I get? Good. 9 pi. Good. Times good old chain rule, thank God. And what's going to keep you remembering this is it's what they're asking you. So you know it's got to show up. And if it doesn't show up, how the hell could you ever answer the question? Now you plug stuff in. So what's this? 2. And of course h is 5. And now I can solve for dh dt. You get whatever the hell. At this point, I don't care. Let's see. 8 over 9 pi, I think it is. Yeah, 8 over 9 pi. What are the units on this? Yeah, centimeters per second. And then you can make it a decimal, it's fine. Right? We can speak like humans. How quick is I changing? 8 over 9 pi. Who the hell are you? So you can make it a decimal, that's fine. Okay. All right. Is that decent? You guys remember that kind of stuff? Related rates was the first place I brought in the idea of tell me, ask me. And that happens so often in math. Because they happen again in the optimization section, section 4.7. Find the maximum area of this thing or whatever, or the minimum cost. You guys are also allowed to ask follow-up questions. That's fine. All right. So that's all right. Where else do we want to go with this? What else do we want to look at? Oh yeah, See that last problem, number 13, just to point this out? That's the volumes of revolution problems. I just got lazy and figured I'd pick some out of the review section from that chapter, so I didn't have to try to set them all up. Yeah, 8.1, no homework there. I just wanted to throw the idea at you because that idea is used in broader terms later. And it's a relatively simple setup, but what's weird about, so notice how we go to chapter 8, but that's after, and the first chapter you do in Calc 2 is chapter 7. And so many problems in chapter 8 require what you learn in chapter 7 to do. So really, the stuff we do in chapter 8 is supposed to be just introductory surface level stuff anyway. Yeah. You're not going to be able to do a lot of problems until you learn more methods besides just U sub. U sub is awesome, but it's not very powerful. It needs everything to be just right already. There are more powerful things you learn in Calc 2 in Chapter 7. So let me tell you, all right. So I know some of you guys don't like me much, but here's how I study. Just so you, how I used to study when I was taking courses. I would write down the concepts from each chapter that we're supposed to know. And I would kind of make sure I felt comfortable with each one. So I try to find a problem that dealt with an idea and make sure I was comfortable with that idea and move on. And I would get to the point where somebody could say, washers, and I would go, that's in section this. What about related rates? That's section this. What about that section? I knew where they were in the book. That's how much I kind of looked them over. I hope, one thing I really hope you got from this class is how important ideas are. They are more important than specific procedures. Specific procedures make you feel comfortable. Teachers can create tests that only go the steps they ever showed you, and that doesn't really mean you learned shit, right? Ideas are most important. The more you understand an idea, the easier the process is going to be, because then it just makes sense. It's not memorization, it's just doing what makes sense. You can't make it very far in math if you're stuck on thinking you have to memorize everything. Holy shit, there's way too many things to memorize. Thank God they're all connected by a few basic ideas. Well, not basic, but a few fundamental ideas. Yeah. Yeah, all right. Yeah, I forgot about 6.5. Thank you. I forgot we didn't actually cover that. 6.5 is almost too nice to believe. I don't know if anybody's tried that section out yet. I don't blame you if you haven't. Yeah, 6.5 is still something you need to do. I forgot we didn't do that yet. All right. 6.5 is almost like the book is saying, man, we're sorry for the intense shit you just did. Here's a gimme. So now watch, this is kind of nifty. If I have a function, I'm just going to make it, whatever we come up with here will be still true. I want to know the average value of that function between A and B. So I want to know how tall on average is it across that region. So let me ask you this. Let me say that, let me give you a more specific situation. So say this is 2 to 7. And let me tell you that the area of this little piece, the area of this piece is what, Jeff? Is 15. This idea is so desperately beautiful. Now, how normally would we have to calculate that area? What would we do? If I gave you the function, how would you calculate the area between 2 and 7? You would do what? Integrate it from 2 to 7. Now look, but I'm just going to tell you, the area is 15. Somebody already did that work for me. The area is 15. So the idea is I want to see what's the value that is the average height. So maybe it's about, it's okay, Jeff, doesn't have to be. Maybe it's about right there. So that kind of fills this in. So maybe that's the average height. It's below that, above that, and it averages there. One way to get that is if I could just take this area and make it into a rectangle, I could tell what that average height is. Do you guys see that? If I could take this area and make it into a rectangle, I could see what that height is. And really, let me come at it a different way. How do you average a bunch of numbers anyway? What do you do to average numbers? Add them all up. Divided by? N. Okay. So divided by the total number. Right? I like it. So in calculus, this of course is integral, which would be the area, divided by the total number would be the width. That's how far it ranges over. So how would I find the average value? Well, what would this be? What would this height be for the related rectangle? Can anybody figure out what that height is? How wide is it? How wide is it? 5. And what's the area? 15. So what's the height? 3. You took the average, you took the sum, the area, divided by the total. That's how you got the average value. So what's it look like? And if they give you a function, and they say find the average value of that function, how do you do that? You integrate the function divided by how far it goes. And what that really visually does is it smooshes out into a rectangle and just sees what the height is. That would be the average value of the function. All right, it is almost too nice to believe. So if you can integrate, you can then take that number and divide by the distance. So it's really like one measly step added to section 5.4, which is where you did, or section 5.3, I think, definite intervals. You do the definite interval, one more step, you divide by whatever the difference of those is. That's it. Just adds that one step on. So it makes visual sense, it makes definition sense. Add them all up, divided by how many there are. All right. So 6.5 really comes down to just more integration practice, to be honest. That's all it is. Yeah. Oh, yeah. Sure. If you want to make efficient use of your time, you can pick another problem out in the practice final, give it a go. We could do it together then. You can work on corrections to the last test and ask me questions you have as you try to do them.